At the heart of our solar system blazes a yellow dwarf star that we call the Sun. This massive, glowing sphere of hot gas is the central anchor of everything that orbits it, and it is by far the largest object in our solar system. With a diameter of roughly 1.4 million kilometers, the Sun is so enormous that over 1 million Earths could fit inside it. Its mass is equally staggering, more than 330,000 times that of our planet. An object with such mass naturally produces an enormous gravitational pull, a force that draws all massive objects toward it. It is this very gravity that keeps the planets, asteroids, and comets bound to the Sun, tracing their elliptical orbits through space. Without it, our solar system would unravel, leaving planets adrift in the cold void. Beyond its gravitational influence, the Sun is the primary source of energy for our world. Its light and warmth sustain life, drive weather systems, power photosynthesis in plants, and regulate climate. But imagine, just for a moment, a universe in which the Sun disappeared and was replaced by something far stranger, a black hole. Black holes are among the most enigmatic objects in the cosmos, with gravitational fields so intense that even light cannot escape their pull. They come in various types, depending on their origin, mass, and size. The most common black holes are stellar black holes, born when massive stars reach the end of their life cycles. Stars, over millions or billions of years, burn their nuclear fuel, expanding, cooling, and changing color as they age. When a particularly massive star exhausts its energy, it may explode in a cataclysmic event known as a supernova, briefly outshining entire galaxies. Following this violent death, the remnant core may collapse under its own gravity into an incredibly dense point known as a singularity, surrounded by the event horizon, a spherical boundary beyond which nothing can escape. The event horizon is often called the point of no return. Any object crossing it is inexorably pulled toward the singularity, disappearing from the observable universe. Not every star is capable of forming a black hole. Astronomers often measure stars in relation to the Sun, and only stars at least 8 times more massive than the Sun can undergo supernova explosions, while stars around 20 times the Sun's mass or more may collapse into black holes. In other words, our Sun is far too small to end its life as a singularity. However, for the sake of exploration, let us imagine a hypothetical scenario in which the Sun vanishes and is replaced by a black hole of equivalent mass. This mini black hole would be unusual, with just a single solar mass, making it far smaller than typical black holes, which often contain several solar masses or more. Although black holes formed from stellar evolution typically have a lower mass limit of about 2.5 to 3 solar masses, the theoretical concept of a 1 solar mass black hole is not entirely impossible, especially considering the hypothesized existence of primordial black holes, which could be even smaller. Black holes are astonishingly compact. The first widely confirmed stellar black hole, Cygnus X-1, contains 21 times the Sun's mass, yet its event horizon measures only about 124 kilometers across, less than 1% of Earth's diameter. A black hole of 1 solar mass would have an event horizon only about 6 kilometers wide, over 2,100 times smaller than Earth, while containing 330,000 times its mass. Despite the compactness and extreme density, such a small black hole would not necessarily pose an immediate threat to the solar system. Popular culture often misrepresents black holes as cosmic vacuum cleaners, indiscriminately sucking up matter. In reality, at a distance, their gravitational influence behaves just like that of any object with the same mass. Newton's shell theorem explains that a symmetrical mass distribution, whether spread out in a star or condensed into a singularity, affects external objects in the same way. Planets orbiting a 1 solar mass black hole would follow the same paths they do around the Sun, maintaining the overall structure of the solar system. While gravity might remain unchanged, the disappearance of the Sun would set off catastrophic consequences in other areas. The Sun constantly emits charged particles in the form of solar wind, which extends well beyond the orbit of Pluto and creates a protective bubble around the solar system called the heliosphere. This magnetic shield deflects dangerous cosmic rays and interstellar radiation that could otherwise bombard planets. Without the Sun, this protective bubble would vanish, allowing high-energy particles to flood the solar system. Such radiation could ionize planetary atmospheres, alter climate systems, and increase the radiation exposure of all living organisms on Earth. Though planets might remain gravitationally stable, the absence of the sun's energy would trigger environmental and biological collapse. The sun produces energy through nuclear fusion, a process in which hydrogen nuclei fuse to form helium, releasing tremendous energy across the electromagnetic spectrum. Approximately 40 to 50% of this energy is visible light, giving us the warm, life-sustaining sunlight we feel. The remainder is emitted as infrared or ultraviolet radiation, which is invisible to the human eye. A black hole, in contrast, produces no visible light. If the sun were replaced by a black hole, Earth and the other planets would gradually plunge into darkness. Light from the sun would continue to reach Earth for about 8 minutes and 20 seconds, the time it takes to traverse the distance between our star and our planet. But once those last photons passed, a lingering twilight from reflected light on the moon and other planets would fade, leaving Earth in a permanent night. Even the moon and planets would vanish from view, leaving only the faint glow of distant stars. The loss of sunlight would also bring a dramatic drop in temperatures. Earth's average surface temperature of 15 degrees Celsius would fall steadily. Greenhouse gases and geothermal heat could provide minimal warmth, but these sources would be insufficient to sustain habitable conditions. Tropical regions would freeze, oceans would solidify at the surface, and ice would spread across much of the land. Only the deepest ocean trenches and areas near geothermal vents might retain liquid water, insulated by layers of ice above. Life on the surface would face its most extreme challenge. Photosynthetic plants would die within days, interrupting the food chain. Herbivores would starve, followed by predators, leading to widespread extinction. A few species could survive temporarily by scavenging or residing near deep-sea vents, but most ecosystems would collapse. Rainforests, coral reefs, and other complex environments would crumble, leaving the planet largely barren. Humans, initially, might survive the initial darkness, but as temperatures plummet, society itself would face collapse. Infrastructure would fail, pipelines might freeze and burst, power grids would fail, and food production would cease as crops froze and livestock perished. Supply chains would crumble, causing widespread shortages and societal disruption. Over time, human populations would decline dramatically. Yet, with ingenuity, small groups could adapt, using nuclear or geothermal energy to generate heat and electricity, building underground shelters to insulate themselves from the extreme cold, and restructuring communities to survive without sunlight. In essence, humanity could persist, but only by confronting the most formidable natural challenge in its history. Even though this scenario is terrifying, the reality is reassuring. The sun is not massive enough to ever become a black hole and is expected to continue its steady, life-giving glow for at least another 5 billion years. Our star's light, heat, and gravity will remain the foundation of life and stability in the solar system for countless generations. While contemplating a sudden replacement of the sun by a black hole illustrates the extremes of cosmic physics, it also highlights the remarkable balance that allows life to flourish on Earth. The sun is far more than just a luminous ball in the sky. It is the heartbeat of our solar system. Its energy drives weather and ocean currents, fuels photosynthesis, and regulates the climate. Its gravity maintains the orbital dance of planets, asteroids, and comets, and its magnetic field protects life from the harsh radiation of interstellar space. Without it, Earth would descend into darkness, cold, and chaos, a frozen world where life could barely survive. Understanding the sun and the consequences of its absence reminds us of the delicate balance of forces and processes that sustain life on our planet and underscores the extraordinary role our star plays in the cosmic order. Even when we look at black holes, objects of almost unimaginable density and gravitational pull, we see that their influence is not uniform and indiscriminate. Their power is profound near the event horizon, but at a distance, their gravity behaves just like any other object of equal mass. This principle reinforces the understanding that the cosmic forces shaping our solar system are both predictable and delicate, a balance that has allowed life to evolve over billions of years. Black holes are fascinating and terrifying, yet they also highlight the resilience and order of the universe. A universe in which the sun will continue to shine for billions more years, nurturing the planets and life that depend on it. In the end, while imagining a black hole replacing the sun can spark curiosity and even fear, it is also a reminder of how remarkable our solar system is. The sun is both fragile and mighty. Fragile in its ability to sustain life, yet mighty in its gravitational and energetic presence. The delicate equilibrium of mass, energy, and motion in the solar system is what makes Earth habitable, allowing life to persist in a cosmic environment that can otherwise be harsh and unforgiving. By studying stars, black holes, and the laws of physics that govern them, we not only satisfy human curiosity, but also gain a profound appreciation for the extraordinary star that continues to illuminate our world, guiding life on Earth through the